So we are going to learn about extended Euclidean algorithm. It is used to find the modular inverses when you are talking about modular arithmetic with respect to prime numbers. This is like closely related to Euclid's algorithm to find GCD. With respect to primes, like in this case, number 19 is a prime number. So 14 is a positive number which is less than 19. So we can say for sure that GCD of both of them is equal to 1, because if a number is divisible, then it cannot be prime, and we can verify that 19 is prime. So the idea is that if we can do we can reverse the Euclidean algorithm to find an equation of this form. Okay, so we can say that there is a coefficient called s and t, such that this s dot t stands for such that. Okay, so the coefficients s and t such that 14 times s plus 19 times t is equal to 1. So how do we know it? We can do the Euclidean algorithm, right? So we can say 19 is equal to 1 times 14 plus the remainder 5. 14 will be 2 times 5 plus remainder 4, and 5 is equal to 1 times 4 plus 1. So 1 is the GCD, because in the next step you are going to get 4 is equal to 1 times 4 plus 0. This is like not really necessary. Okay, but from this, the thing is that we are going to rewrite these equations. We are going to rewrite 5 as 19 minus 1 times 14, 4 as 14 minus 2 times 5. I mean, in every step we are moving the remainder to the left hand side. Okay, so from this we can get 1 is equal to 5 minus 1 times 4. What we are going to do is we are going to substitute for 4 in this equation. So if we name these equations 1, 2 and 3, so we are going to substitute for 4 in 3, and we will get 1 is equal to 5 minus 1 times 14 minus 2 times 5. And so we can simplify this by writing 1 is equal to, and pay close attention here. So if we multiply minus 1 inside, we get minus 2 times minus 1 is 2. Okay, we get 2 times 5. We don't want to actually simplify these coefficients. We don't want to multiply 2 times 5 is equal to, we don't want to write that, because we want to get this form. Okay, so we can basically write 3 times 5 here. Okay, 3 times 5 minus 1 times 14. But from equation 1, we can say that 5 is equal to 19 minus 1 times 14. So if we substitute that, we will get 1 is equal to 3 of 5 is equal to 19 minus 1 times 14 minus 1 times 14. Okay. From this, we can get, so 3 times minus 3 will be minus 3. And here there is minus 1 times 14. So minus 3 plus minus 1 is minus 4. And 3 times 19 is 3 times 19. So we can get basically 1 is equal to 3 times 19 plus minus 3 minus 1 minus 4 times 14. Okay. We can verify this. How can we verify this? Right. So 3 times 19 is equal to 57. 4 times 14 is equal to 56, and if we take if we subtract them, we will get like 57 minus 4 is equal to 57 minus 16, 56. 57 minus 56 is equal to 1. Simple math. But so we can say that negative 4 is the multiplicative inverse of 14 in this group Z19. But in the Z19 group, we only have positive numbers 0, 1 up to 18. When we know that 19 is basically a 0, okay, because 19 divided by 19 is 0, the remainder is 0, right? So we can say that negative 4 is actually congruent to 19 minus 4 is 15. So 15 mod 19, right? And we are saying that negative 4 is the multiplicative inverse, which means 15 should be the multiplicative inverse of 14. We can verify that also. 15 times 14 will be 22. 4 plus 2 is 6. 5, 1. This will be 0, 11, 210. 210 when divided by 19, what is the remainder? That's the question that we're asking. Okay. So when you try to divide 210 by 19, that will be 1 times 20. That will be, so the idea is 210 is simply 210 is equal to 11 times 19 plus 1. Okay, you can 10 times 19 is 190, 190 plus 19 is 209, so 209 plus 1. And here we have verified that 15 is indeed the multiplicative inverse of 14, because 15 times 14 is 210, which is congruent to, this means 210 is congruent to 1 mod 19. 210 is nothing but 14 times 15 is congruent to 1 mod 19. Okay. So indeed we get the multiplicative inverse of 15. So we need to do this kind of like substitution, okay, to actually get the multiplicative inverse. In the previous video, I showed you the pseudocode to get the GCD of given two numbers. So there, that pseudocode does not actually, give you the multiplicative inverse. So in order to do that, we need to do some mathematical derivations. Okay. So take some time, pause the video, make sure that you have understood the process so far. Okay. Now what we are going to do is what I call a symbolic reasoning. The idea is that if we know that D is the GCD of A and B, we can write D in this form. D is equal to A times S plus B times T, where S and T are the coefficients. So these coefficients are called Bézout coefficients to honor the mathematician. Okay. We know this because we know that Euclidean algorithms works, and if we redo the Euclidean algorithm in certain way, we can get this form. Right? We know that. So we are just going to assume that these arbitrary integers S and T exist, which satisfies this equation. Okay. And we are going to do some naming tricks. We are going to say that R0 is equal to A and R1 is equal to B. And here we are just assuming that A is greater than B. That's not necessarily, that's not really necessary, but we can just assume that. Okay, we can just shuffle the numbers, right? If A is less than B, we can just shuffle the numbers, right? And we can continue our process. We can write R0 as 1 times A plus 0 times B. If this is allowed, makes sense, right? Because R0 is just A. R1 as 0 times A plus 1 times B, makes sense. And now we are going to do this process, right? So in every step we get a new reminder, okay? And then that new reminder will be the divisor in the next step, right? So we are just going to say that for any remainder Ri in this particular process, there exist integers Si and Ti such that Ri can be written in this particular form. Okay, we know this, right? We also know that Ri minus 2 is how Ri minus 2 and Ris related, right? So Ri minus 2 is equal to some quotient into Ri minus 1 plus Ri. Okay. Ri minus 1 is the remainder in the previous step, right? So in the next step, Ri minus 1 will be the divisor and Ri will be the new remainder. If you have a confusion, just go back, take a paper and pencil, go back to try some examples and name these R0, R1, R1, R0, R1, R2, right? The numbers, you will understand this. Okay, but with this we can do. So I'm just going to rearrange this. Ri is equal to Ri minus 2 minus Qi times Ri minus 1. So what we have that Ri is equal to A times Si plus B times Ti. From this we can write Ri minus 1 I'm just assuming that si minus 1 and ti minus 1 variables exist, okay, because we know it exists. Similarly, for ri minus 2, we are also going to say that si minus 2 and ti minus 2 exist such that this equation is satisfied, okay. And we have this equation, right? We just rewrote this in the previous step. Now I'm going to simply substitute the values of ri minus 2 and ri minus 1 in this right hand side because we are solving for ri, okay. So ri stays in the left hand side as it is. In place of ri minus 2, I have substituted this, okay. In place of ri minus 1, I have substituted this. And the qi is in the outside, right? Just like this. No, like just direct substitution. Now what we are going to do is, we are going to take the common factors a of these two terms, okay, and we are going to separate b also. So simply if we take a out of here, we have si minus 2 minus qi times si minus 1, and here we have ti minus 2, this one, minus qi times ti minus 1. So now we have a working formula, okay, working recursive formula. And we know that S0 should be 1, T0 should be 0, and S1 should be 0, T1 should be 1. That is simply what we get by writing R0 is equal to 1 times A in the very first equation that we derived, plus 0 times B, because we are assuming R0 is equal to A, okay, and R1 is equal to 0 times A plus 1 times B, right. So we can say this is S0, okay, so this is T0. So this is the base condition for this recursive formula. So we have a recursive formula and we have the base condition, and from that we can write our pseudocode, okay, algorithm. So S0 is 0, old S is 1, okay, old S in the sense, old S is actually S0, okay, at this very step, old S is, let me use a different color. So old S is S0, okay, so this is actually S1, this is T1, old T will be T0, right. So we have this, and we set the R to be, the first we use B as the divider, right? So old R is A, kind of like that, okay? Now in this particular first step, we are using, we are going to divide with B, and we are going to get the remainder, and we update it, okay? So we will divide with the current R with the old R, like the previous step. And similarly, we update all the variables with respect to the equations that we derived in the previous steps. At the end, when we will stop when actually remainder is equal to 0. So the coefficients before the 0 step, the remainder before the 0 remainder actually is the GCD. So we are going to use that old S and old T to get our answer. So old R, that will be the GCD. So the old S and old T, that will be the Bézout coefficients. Okay. And yeah, so T will be, if you consider A as the prime, then T will be the multiplicative inverse. So you can visit this website, brilliant.org. This is an excellent resource to sharpen your basics mathematical skills, right? But this is paid, but you are going to learn a lot, okay? Which I won't be able to cover all the basic fundamentals of the maths here, but I'm just going to I'm just pointing you in the right direction. And this is the particular web page where they discuss about the extended Euclidean algorithm in depth. So we are going to, the thing is, in the SCP-256K1 implementation, as it is used in the Bitcoin core, Euclidean algorithm is not used there. That they use something called safe GCD, which is a later development, which is an improvement on the Euclidean algorithm, which is an improvement on the extended Euclidean algorithm as well, to find the multiplicative inverse. Okay. So if you are paying close attention, okay, you can try to find the GCD of different numbers using Euclidean algorithm. For some cases, the number of steps taken will be like 2 or 3, in even 1. But for other cases, the number of steps taken might be like, you might take like 10 steps if you are considering some very big number, okay, big numbers with some edge cases. That might even take like something like 10 steps. Okay, so the thing is that if you are using the Euclidean algorithm, okay, there is the timing difference for different inputs. That's the idea. And that might not be like favorable in a cryptographic sense. Okay. And that might lead to something called a side channel attack. So Safe GCD fixes this, and we will have a discussion about side channel attack as well. Okay. Hope this keeps you interesting and motivated to learn more.